What if everything we think we know about the universe is just the tip of the iceberg? Imagine staring into the night sky, only to realize that the stars and galaxies we see make up less than 5% of what's actually out there. The rest, a vast, invisible realm of mysteries that science is still struggling to explain. From forces that defy gravity to cosmic anomalies that rewrite the rules of physics, the universe is filled with puzzles that leave even the brightest minds scratching their heads. Today, we're diving into 25 of the most baffling mysteries of the universe phenomena that challenge our understanding of reality itself. These aren't just questions without answers, they're doorways to a deeper, more mysterious cosmos. So are you ready to explore the unknown? Let's begin. Now, let's step into the shadowy realm of the cosmos, where the first mystery awaits: dark matter. Imagine a universe where most of what exists is completely invisible. That's the reality we're dealing with when it comes to dark matter. Scientists estimate that dark matter makes up about 27% of the universe, yet it doesn't emit, absorb, or reflect light. It's completely invisible to our telescopes and instruments. So how do we even know it's there? The answer lies in gravity. In the 1930s, astronomer Fritz Zwicky noticed something strange while observing galaxy clusters. The galaxies were moving so fast that, according to the laws of physics, they should have flown apart, but they didn't. Something unseen was holding them together with its gravitational pull. Zwicky called this mysterious force dark matter, and the name stuck. Decades later, Vera Rubin's observations of rotating galaxies provided even more evidence. Stars on the outer edges of galaxies were moving just as fast as those near the center, defying expectations. The only explanation, an invisible mass, dark matter, was exerting its gravitational influence. But here's the kicker: despite knowing it exists, we still can't directly detect it. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic interference, hoping to catch a glimpse of dark matter particles. Yet, so far, nothing. It's like trying to catch a ghost with your bare hands. Theories suggest dark matter could be made of weakly interacting massive particles, or WIMP, but these particles remain elusive. Some even propose that dark matter might interact with forces we don't yet understand, making it even harder to pin down. This invisible enigma isn't just a cosmic curiosity, it's the scaffolding of the universe. Without dark matter, galaxies wouldn't have formed, and the universe as we know it wouldn't exist. Yet, its true nature remains one of the greatest unsolved puzzles in science. What is it made of? How does it interact with the rest of the universe? These questions keep physicists up at night, searching for answers in the dark. And as we move forward, this mystery only deepens, reminding us just how much we have yet to uncover. Next, we'll turn our attention to another invisible force shaping the cosmos: dark energy. But for now, let's sit with the idea that most of the universe is hidden in plain sight, waiting to be discovered. Now, let's shift our gaze to another invisible force that's reshaping the cosmos: dark energy. If dark matter is the unseen glue holding galaxies together, dark energy is the mysterious force pushing the universe apart at an ever-increasing speed. Discovered in the late 1990s, dark energy completely upended our understanding of the universe's fate. Instead of slowing down after the Big Bang, the expansion of the universe is speeding up, and dark energy is the prime suspect behind this cosmic acceleration. So, what exactly is dark energy? The truth is, we don't fully know. It's not a substance like dark matter, but rather a property of space itself. Think of it as an invisible energy woven into the fabric of the universe, acting like an anti-gravity force. Albert Einstein actually predicted something similar in his theory of general relativity, calling it the cosmological constant. He later dismissed it as his greatest blunder, but modern observations suggest he might have been onto something after all. The discovery of dark energy came from studying distant supernova exploding stars that serve as cosmic mile markers. Astronomers expected these supernovae to appear dimmer if the universe's expansion was slowing down. Instead, they were brighter, indicating the universe was expanding faster than ever before. This shocking revelation earned the researchers the Nobel Prize in Physics in 2011, but it left us with more questions than answers. Today, dark energy is estimated to make up about 68% of the universe, dwarfing even dark matter. Yet, its true nature remains one of the biggest mysteries in science. Some theories suggest it's a constant energy density filling space, while others propose it's a dynamic field that changes over time. There's even the possibility that our understanding of gravity itself is incomplete, and dark energy is a sign that we need to rethink the fundamental laws of physics. What makes dark energy so perplexing is that it's not just a scientific curiosity, it's shaping the ultimate fate of the universe. If it continues to dominate, the universe could keep expanding forever, leading to a cold, dark, and lonely end known as the Big Freeze. But if dark energy behaves differently over time, the universe's fate could take a completely unexpected turn. As we grapple with these questions, one thing is clear: dark energy is a reminder of how much we still don't understand about the cosmos. It's a force that defies explanation, challenges our theories, and keeps scientists searching for answers. And as we move forward, this mystery will continue to shape our quest to understand the universe's deepest secrets. Next, we'll journey back to the very beginning of everything, the Big Bang, and explore the unanswered questions surrounding the birth of our universe. Now, let's rewind the cosmic clock to the very beginning, the Big Bang. This monumental event is often described as the birth of the universe, but it's far from a simple story. The Big Bang theory tells us that around 13.8 billion years ago, the universe exploded into existence from an unimaginably hot and dense state. But what exactly caused this explosion, and what, if anything, existed before it? These are questions that continue to baffle scientists and spark endless debate. The Big Bang theory is supported by a wealth of evidence, from the cosmic microwave background radiation, the faint afterglow of the explosion, to the observed expansion of the universe. Yet, despite its success, the theory leaves some glaring gaps in our understanding. For instance, what triggered the Big Bang in the first place? Was it a random quantum fluctuation, or is there a deeper mechanism at play? And if the universe began from a single point, what was there before that point? The concept of before might not even apply, as time itself may have started with the Big Bang. Another mystery is the uniformity of the universe. Observations show that the cosmos is remarkably consistent in all directions, a phenomenon known as the horizon problem. How did regions of the universe that are now billions of light-years apart manage to reach the same temperature and density without ever being in contact? One leading explanation is cosmic inflation, a rapid expansion of space in the universe's earliest moments. But while inflation solves some problems, it also raises new ones, like what caused it and why it stopped. Then there's the question of what the Big Bang actually was. Was it truly an explosion, or is that just a metaphor for something far more complex? Some scientists suggest that the Big Bang might have been a transition from a previous state of the universe, rather than an absolute beginning. Others propose that our universe is just one of many in a vast multiverse, with each universe experiencing its own Big Bang. Despite these unanswered questions, the Big Bang remains the leading theory because it provides the best framework for explaining the universe's evolution. It's a story that ties together the formation of galaxies, the distribution of elements, and the very fabric of space and time. Yet, it's also a story that reminds us how much we still have to learn. The Big Bang isn't just a theory about the past, it's a gateway to understanding the fundamental nature of reality. As we ponder these mysteries, we're reminded that the universe is far stranger and more complex than we can imagine. And with every discovery, we inch closer to unraveling the secrets of our cosmic origins. Next, we'll explore a mystery that's closer to home, or at least closer to our search for life beyond Earth, as we dive into the Fermi paradox and the question of why we haven't found extraterrestrial life. Shifting our gaze from the origins of the universe to the possibility of life beyond Earth, we encounter one of the most perplexing questions in science, the Fermi paradox. Named after physicist Enrico Fermi, who famously asked, "Where is everyone?" This paradox highlights the contradiction between the high probability of extraterrestrial civilizations existing in the vast universe and the complete lack of evidence for their existence. Given the sheer size of the cosmos with hundreds of billions of galaxies, each containing hundreds of billions of stars, it seems almost certain that life should have emerged elsewhere. Yet, despite decades of searching, we've found no definitive signs of intelligent life. So, where is everyone? This question has sparked a range of theories, each attempting to explain the eerie silence. One of the most compelling explanations is the Great Filter hypothesis. This idea suggests that there's some kind of barrier, a filter, that prevents civilizations from reaching a stage where they can communicate across the stars. This filter could occur at any point in a civilization's development. For instance, it might be incredibly rare for life to emerge in the first place, or perhaps advanced civilizations inevitably destroy themselves before they can make contact. If the Great Filter lies ahead of us, it could mean humanity is on the brink of a catastrophic event. If it's behind us, we might be one of the rare exceptions to have made it this far. Another theory is the rare Earth hypothesis, which argues that the conditions necessary for complex life are far more unique than we assume. While simple life might be common, the combination of factors needed for intelligent life, such as a stable star, a protective magnetic field, and a moon to stabilize the planet's rotation, could be exceedingly rare. Earth might be a cosmic anomaly, a one-in-a-billion fluke that allowed life to flourish. There are also more optimistic explanations. Some scientists suggest that advanced civilizations might be deliberately avoiding contact, either to protect us or to observe us without interference. Others propose that we're simply not looking in the right way. Perhaps extraterrestrial life communicates through methods we haven't yet discovered, or they exist in forms we can't recognize. The Fermi paradox forces us to confront profound questions about our place in the universe. Are we alone, or is the cosmos teeming with life we've yet to find? Each theory offers a glimpse into the possibilities, but none provide a definitive answer. As we continue to search the stars, the mystery of the Fermi paradox reminds us that the universe is full of surprises, and that the truth might be stranger than we can imagine. Next, we'll venture into the enigmatic realm of black holes, where the laws of physics as we know them begin to break down, and the universe reveals some of its most bizarre secrets. Now, let's turn our attention to one of the most fascinating and mysterious phenomena in the universe, black holes. These cosmic enigmas are regions of space where gravity is so intense that nothing, not even light, can escape their pull. But how do black holes form, and what secrets do they hold within their dark hearts? Black holes are born from the dramatic deaths of massive stars. When a star many times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against the crushing force of its own gravity. The star collapses in on itself, triggering a supernova explosion. What remains is an incredibly dense core, so compact that it warps space and time, creating a black hole. At the center of this black hole lies the singularity, a point where the laws of physics as we know them break down. Here, density becomes infinite, and our understanding of reality reaches its limits. But the mysteries of black holes don't stop at their formation. One of the most puzzling aspects is the concept of information loss. According to quantum mechanics, information about the state of particles cannot be destroyed. Yet, when matter falls into a black hole, it seems to vanish completely, leaving no trace. This contradiction, known as the information paradox, has baffled scientists for decades. Does the information truly disappear, or is it somehow preserved in a way we don't yet understand? Adding to the intrigue is Hawking radiation, a phenomenon predicted by physicist Stephen Hawking. Black holes aren't entirely black. They emit tiny amounts of radiation due to quantum effects near their event horizons. Over time, this radiation causes black holes to lose mass and eventually evaporate. But here's the catch: if a black hole evaporates completely, what happens to all the information it swallowed? This question remains one of the greatest unsolved problems in theoretical physics. Black holes also challenge our understanding of space and time. Near the event horizon, the boundary beyond which nothing can escape time appears to slow down dramatically. For an outside observer, an object falling into a black hole would seem to freeze in place, never quite crossing the horizon. Yet, for the object itself, time would continue as normal, leading to a bizarre disconnect between perspectives. These cosmic giants are not just theoretical curiosities. They play a crucial role in shaping the universe. Supermassive black holes, millions or even billions of times more massive than the Sun, lie at the centers of galaxies, including our own Milky Way. They influence the motion of stars and gas, and their immense gravity can even bend light, creating the phenomenon known as gravitational lensing. As we continue to study black holes, they reveal more questions than answers. From the nature of singularities to the fate of information, these cosmic mysteries push the boundaries of our knowledge. They remind us that the universe is far stranger and more complex than we can imagine, and that every discovery brings us closer to understanding the true nature of reality. Next, we'll explore the mind-bending concept of the multiverse, where the idea of parallel universes challenges everything we think we know about existence. Now, let's venture into one of the most mind-bending ideas in modern science, the multiverse theory. Imagine a reality where our universe is just one of countless others, each with its own unique set of physical laws, constants, and even histories. This concept, while sounding like science fiction, has a surprising amount of scientific backing, though it remains one of the most debated topics in cosmology. The multiverse theory arises from several areas of physics, including quantum mechanics, string theory, and cosmology. One of the key ideas comes from quantum mechanics, where every possible outcome of a quantum event might exist in its own separate universe. For example, if you flip a coin, in one universe it lands heads, and in another it lands tails. This interpretation, known as the many worlds theory, suggests that every decision or random event spawns a new universe, creating an infinite web of parallel realities. Another foundation for the multiverse comes from cosmic inflation, the rapid expansion of the universe just after the Big Bang. Some scientists propose that inflation didn't stop everywhere at once. Instead, it continues in certain regions, creating bubble universes that are disconnected from our own. Each of these bubbles could have different physical properties, leading to a vast array of universes with varying laws of physics. String theory, a framework attempting to unify all fundamental forces, also hints at the possibility of a multiverse. According to this theory, there could be as many as 10 to the power of 500 different configurations of the universe, each with its own unique set of dimensions and physical constants. This staggering number suggests that our universe might just be one tiny corner of a much larger, more complex multiverse. But how do we prove the existence of these parallel universes? This is where the multiverse theory faces its greatest challenge. Since these universes are, by definition, beyond our observable reach, direct evidence is nearly impossible to obtain. However, some scientists suggest that indirect clues might exist. For instance, if two bubble universes collided in the distant past, the impact could leave a detectable imprint on the cosmic microwave background, the afterglow of the Big Bang. So far, no such evidence has been found, but the search continues. critics argue that the multiverse theory is untestable and therefore falls outside the realm of science. Without the ability to observe or interact with other universes, some say it remains more of a philosophical idea than a scientific one. Yet, proponents counter that the multiverse could explain some of the deepest mysteries of our universe, such as why the fundamental constants of nature seem so finely tuned for life. If there are countless universes, each with different constants, it's not surprising that at least one ours would have the right conditions for life to exist. The multiverse theory challenges our understanding of reality, pushing us to consider possibilities far beyond our everyday experience. Whether it's a cosmic reality or a fascinating thought experiment, it reminds us that the universe or multiverse is far stranger and more complex than we can imagine. Next, we'll unravel the mysteries of time itself, exploring why it flows in one direction and whether time travel could ever be possible. Now, let's turn our attention to one of the most fundamental yet puzzling aspects of our universe, the nature of time. Time is something we all experience every day, yet it remains one of the greatest mysteries in science. Why does time flow in one direction? Could time travel ever be possible? And how does time interact with gravity? These questions challenge our understanding of reality itself. First, let's tackle the arrow of time. In our everyday lives, time seems to move forward in a straight line from past to present to future. But why is this the case? The laws of physics, as we understand them, are mostly time symmetric, meaning they work the same whether time moves forward or backward. So, what gives time its direction? The answer lies in a concept called entropy, which is a measure of disorder in a system. According to the second law of thermodynamics, entropy always increases over time. This increase in disorder is what gives time its arrow, creating a clear distinction between past and future. Think of it like a shattered glass. It's easy to break, but nearly impossible to put back together. That irreversibility is what drives the flow of time. But what about time travel? Could we ever bend the rules of time and move backward or forward at will? While it sounds like the stuff of science fiction, some theories in physics suggest it might not be entirely impossible. For instance, Albert Einstein's theory of general relativity shows that time is not a fixed universal constant. Instead, it's flexible and can be warped by gravity. Near massive objects like black holes, time slows down, a phenomenon known as time dilation. This raises the tantalizing possibility that, under extreme conditions, time travel might be achievable. One theoretical concept is the idea of wormholes, hypothetical tunnels through space-time that could connect distant points in time and space. However, creating or traversing a wormhole would require exotic forms of matter and energy that we don't yet understand or even know exist. The relationship between time and gravity is another fascinating puzzle. According to general relativity, gravity isn't just a force pulling objects together, it's the curvature of space-time itself. Massive objects like planets and stars warp the fabric of space-time, and this warping affects the flow of time. For example, time passes slightly faster on a mountaintop than at sea level because the gravitational pull is weaker higher up. This effect, though tiny, has been confirmed by incredibly precise experiments. It's a reminder that time and gravity are deeply intertwined, shaping the very structure of our universe. Yet, despite these insights, time remains elusive. Why does it seem to flow at all? Why can't we move backward as easily as we move forward? And what happens to time at the edges of black holes where gravity becomes infinitely strong? These questions push the boundaries of our knowledge, challenging us to rethink our understanding of reality. As we continue to explore the mysteries of time, we're reminded that even the most familiar aspects of our universe can hold profound secrets. Next, we'll dive into the strange and counterintuitive world of quantum entanglement, where particles can be connected across vast distances in ways that defy classical physics. Now, let's step into the bizarre and mind-bending world of quantum entanglement. a phenomenon so strange that even Albert Einstein famously called it spooky action at a distance. Quantum entanglement occurs when two or more particles become linked in such a way that the state of one particle instantly influences the state of the other, no matter how far apart they are. This connection defies everything we know about classical physics, where objects are independent of one another unless they interact directly. Imagine you have a pair of gloves. If you take one glove and send it to the other side of the universe, you instantly know the other glove is its opposite, left or right, without needing to check. In the quantum world, entangled particles are like these gloves, but with a twist. Their properties, such as spin or polarization, are not determined until they are measured. When you measure one particle, its entangled partner instantly assumes a corresponding state, even if it's light years away. This instantaneous connection seems to violate the speed of light, which Einstein's theory of relativity says is the universe's ultimate speed limit. So, how does this work? The answer lies in the peculiar rules of quantum mechanics, where particles exist in a state of superposition, meaning they can be in multiple states at once until observed. When entangled particles are measured, their superposition collapses into a definite state, and this collapse happens simultaneously for both particles, regardless of distance. This phenomenon has been confirmed through numerous experiments, including those using photons separated by hundreds of kilometers. The results consistently show that entangled particles are deeply connected in a way that classical physics cannot explain. But what does this mean for faster-than-light communication? At first glance, it might seem like entanglement could be used to send messages instantaneously across vast distances. However, there's a catch. While the state of one particle instantly affects its entangled partner, this connection cannot be controlled or manipulated to transmit information. The outcome of a measurement is random, so there's no way to encode a message into the entangled particles. This limitation keeps quantum entanglement from breaking the cosmic speed limit set by relativity, but it doesn't make the phenomenon any less astonishing. Quantum entanglement also challenges our understanding of reality itself. It suggests that the universe is far more interconnected than we once thought, with particles sharing a hidden bond that transcends space and time. This has led to profound questions about the nature of existence. Are particles truly separate entities, or are they part of a deeper, unified fabric of reality? And if entanglement allows particles to communicate instantaneously, what does that say about the flow of time and the structure of the universe? As we grapple with these questions, quantum entanglement continues to inspire groundbreaking research, from quantum computing to secure communication networks. It's a reminder that the universe is full of mysteries waiting to be unraveled. Next, we'll explore another cosmic enigma, the Great Attractor, a mysterious gravitational force pulling galaxies toward it at incredible speeds. Now, let's turn our attention to one of the most puzzling gravitational mysteries in the cosmos, the Great Attractor. Hidden deep within the universe, this enigmatic force is pulling entire galaxies, including our own Milky Way, toward it at astonishing speeds. But what exactly is the Great Attractor, and why does it defy our understanding of the universe's structure? The Great Attractor lies in the direction of the constellation Centaurus, roughly 250 million light-years away from Earth. Despite its immense gravitational influence, it remains shrouded in mystery because it's obscured by the dense band of stars, gas, and dust in our own galaxy, known as the zone of avoidance. This makes it incredibly difficult for astronomers to observe directly. What we do know is that it exerts a gravitational pull so powerful that it's drawing galaxies across vast distances, moving them at speeds of up to several hundred kilometers per second. But what could be causing such a massive gravitational anomaly? One leading theory suggests that the Great Attractor is a supercluster of galaxies, a dense region of space packed with thousands of galaxies, each contributing to the overall gravitational pull. The Norma cluster, a massive galaxy cluster at the heart of the Great Attractor, is thought to be a key player in this phenomenon. However, even this supercluster doesn't fully account for the immense gravitational force observed. Some scientists believe there may be an even larger structure behind it, possibly connected to the Shapley supercluster, the most massive concentration of galaxies in the nearby universe. The existence of the Great Attractor raises profound questions about the distribution of matter in the universe. According to the cosmological principle, the universe should be uniform on large scales with matter evenly distributed. Yet the Great Attractor and other massive structures like it challenge this idea, suggesting that the universe is far more lumpy and uneven than we once thought. This has led to new theories about dark matter and dark energy, which may play a role in shaping these cosmic anomalies. Interestingly, the Great Attractor isn't the only force pulling galaxies. Beyond it lies an even more massive structure, the Shapley supercluster, which is tugging on the Great Attractor itself. This cosmic tug of war between these two colossal structures adds another layer of complexity to our understanding of the universe's large-scale structure. It's a reminder that even as we uncover new mysteries, the universe always has more surprises in store. As we continue to explore the Great Attractor, advanced telescopes and observational techniques are helping us peer through the zone of avoidance, revealing more about this gravitational giant. Each discovery brings us closer to understanding not just the Great Attractor, but the fundamental forces that shape our universe. Next, we'll delve into another cosmic puzzle, the Pioneer anomaly, an unexplained deceleration of spacecraft that has left scientists scratching their heads. Now, shifting our gaze from the gravitational mysteries of the Great Attractor, we encounter another baffling phenomenon that has puzzled scientists for decades, the Pioneer anomaly. This strange event involves the Pioneer 10 and Pioneer 11 spacecraft, which, after completing their missions to explore the outer solar system, began to experience an unexpected and unexplained deceleration. Despite being millions of kilometers from Earth, these spacecraft were slowing down in a way that defied the laws of physics as we understand them. The anomaly was first noticed in the 1980s when scientists tracking the spacecraft noticed that they were slightly off course. Over time, it became clear that both Pioneer 10 and Pioneer 11 were slowing down more than they should have been, as if an invisible force was gently tugging them backward. This deceleration was tiny, just a fraction of a millimeter per second squared, but it was consistent and couldn't be explained by known forces like gravity from the sun or planets. So, what could be causing this mysterious slowdown? One theory points to the possibility of dark matter interactions. Some scientists speculate that the spacecraft might be passing through a region of space where dark matter is more concentrated, creating a subtle drag effect. However, this idea remains speculative, as we still don't fully understand the nature of dark matter or how it interacts with ordinary matter. Another explanation suggests that there might be flaws in our understanding of gravity itself. The laws of gravity, as described by Einstein's theory of general relativity, have been incredibly accurate in predicting the behavior of objects in space. But the Pioneer anomaly raises the question, could there be some aspect of gravity that we're missing, especially over vast distances? Some researchers have proposed modifications to the laws of gravity to account for the anomaly, though these theories remain controversial and unproven. Interestingly, the Pioneer anomaly isn't the only instance of unexplained behavior in space. Other spacecraft, like the New Horizons probe, have shown similar but much smaller deviations, adding to the mystery. This has led some to wonder if there's a universal force at play that we've yet to discover, a force that only becomes noticeable over immense distances. Despite decades of investigation, the Pioneer anomaly remains unsolved. Some believe that the answer lies in more mundane explanations, such as heat radiation from the spacecraft's power systems subtly pushing them off course. However, even this theory doesn't fully account for the observed deceleration. As we continue to explore the outer reaches of our solar system and beyond, the Pioneer anomaly serves as a humbling reminder that there's still much we don't understand about the forces that govern our universe. Next, we'll dive into another cosmic enigma, the WOW signal, a mysterious radio signal from deep space that has sparked decades of speculation about extraterrestrial life. Could this be the evidence we've been searching for, or is it just another cosmic coincidence? Now, let's turn our attention to one of the most tantalizing mysteries in the search for extraterrestrial intelligence, the WOW signal. On the night of August 15, 1977, a radio telescope at Ohio State University's Big Ear Observatory picked up something extraordinary, a signal so powerful and unusual that it left astronomer Jerry Amon scribbling, "Wow." In the margins of the data printout, this single, fleeting burst of radio waves has since become one of the most debated and intriguing events in the history of astronomy. The WOW signal lasted for 72 seconds and came from the direction of the constellation Sagittarius. What made it so remarkable was its intensity and frequency. The signal was concentrated at a frequency of 1420 MHz, a range that's often considered a prime candidate for interstellar communication because it's relatively free from interference by natural cosmic phenomena. This frequency is also close to the emission line of hydrogen, the most abundant element in the universe, making it a logical choice for any civilization trying to broadcast their presence. Despite its brief duration, the signal was over 30 times stronger than the background noise, and it matched the characteristics scientists had predicted for an artificial transmission. But here's the catch: the signal was never detected again, despite numerous attempts to find it using more advanced equipment and scanning the same region of space, the WOW signal remains a one-time event. This has led to endless speculation about its origin. Was it a message from an alien civilization, or was it something else entirely? One possibility is that the signal came from a natural astrophysical source, such as a comet or a distant star. However, no known natural phenomenon can fully explain the signal's unique properties. Comets, for example, emit radio waves, but they don't match the frequency or intensity of the WOW signal. Similarly, stars and other cosmic objects don't typically produce such a narrow, focused burst of radio energy. Another theory suggests that the signal might have been a reflection of a human-made transmission bouncing off space debris or a passing satellite. But again, this explanation falls short. The frequency used by the WOW signal isn't commonly used by human technology, and the signal's characteristics don't align with known human-made sources. This leaves us with the tantalizing possibility that the WOW signal was indeed a deliberate attempt at communication from an extraterrestrial civilization. The mystery deepens when we consider the sheer scale of the universe. With billions of stars and potentially habitable planets, the odds of intelligent life existing elsewhere seem high. Yet, despite decades of searching, the WOW signal remains our best and only candidate for a potential extraterrestrial message. Its fleeting nature and unexplained origin continue to fuel debates and inspire new efforts to scan the skies for signs of life. As we ponder the implications of the WOW signal, we're reminded of how much we still have to learn about the cosmos. Could this signal have been our first contact with an alien civilization, or was it just a cosmic coincidence? For now, the WOW signal remains an enduring enigma, a whisper from the depths of space that challenges our understanding of the universe and our place within it. Next, we'll explore another cosmic anomaly that has left scientists scratching their heads: the axis of evil, a peculiar alignment in the cosmic microwave background that seems to defy the fundamental principles of cosmology. What could this mysterious pattern mean for our understanding of the universe? Now, let's shift our focus to another cosmic puzzle that has left scientists both fascinated and perplexed: the axis of evil. This mysterious anomaly in the cosmic microwave background, or CMB, challenges one of the most fundamental principles of cosmology, the idea that the universe is uniform and has no preferred direction. But what exactly is the axis of evil, and why does it defy our understanding of the cosmos? The cosmic microwave background is the afterglow of the Big Bang, a faint radiation that fills the universe and provides a snapshot of the early universe. Scientists have long used the CMB to study the origins and structure of the cosmos, assuming it would be evenly distributed in all directions. However, when researchers analyzed the data, they noticed something strange. Certain patterns in the CMB seem to align along a specific axis, creating what's now called the axis of evil. This alignment suggests that the universe might have a preferred direction, which directly contradicts the cosmological principle. According to this principle, the universe should look the same in all directions on a large scale, with no special points or axes. But the axis of evil hints that this might not be the case. The implications are profound. If the universe does have a preferred direction, it could mean that our current understanding of cosmology is incomplete or even fundamentally flawed. One possible explanation for the axis of evil is that it's a statistical fluke, a random alignment that only appears significant because of the way we're observing the data. However, the odds of such a pattern occurring by chance are incredibly low, leading many scientists to believe there's more to it. Another theory suggests that the anomaly could be the result of gravitational waves or other large-scale structures influencing the CMB. Yet, none of these explanations fully account for the strength and consistency of the alignment. Some researchers have even proposed that the axis of evil could be evidence of a multiverse, a vast collection of universes beyond our own. In this scenario, our universe might be interacting with neighboring universes, creating subtle imprints in the CMB. While this idea is speculative, it highlights how the axis of evil has opened the door to bold new theories about the nature of reality. As we continue to study this cosmic anomaly, one thing is clear: the axis of evil challenges our assumptions about the universe and pushes us to rethink the very foundations of cosmology. Whether it's a clue to a deeper truth or simply a cosmic coincidence, it reminds us that the universe is full of surprises waiting to be uncovered. Next, we'll delve into another mystery that has puzzled astronomers for decades: the Hubble tension, a discrepancy in measurements of the universe's expansion rate that could reshape our understanding of cosmic history. What does this tension reveal about the forces driving the universe apart? Now, let's turn our attention to another cosmic conundrum that has astronomers scratching their heads: the Hubble tension. This mystery revolves around a puzzling discrepancy in how fast the universe is expanding, a measurement known as the Hubble constant. For decades, scientists have used two primary methods to calculate this rate, but here's the catch: they don't agree. This inconsistency, known as the Hubble tension, has become one of the most pressing questions in modern cosmology. To understand why this matters, let's break it down. The Hubble constant is a crucial number in astronomy because it tells us how quickly the universe is stretching apart. It helps us estimate the age of the universe, predict its future, and even understand the nature of dark energy. But when scientists measure this rate using two different approaches, they get conflicting results. The first method involves studying the cosmic microwave background, the afterglow of the Big Bang, which gives us a snapshot of the early universe. The second method looks at nearby objects like supernova and Cepheid variable stars to measure the expansion rate more directly. The problem: these two methods produce numbers that don't match, and the gap between them is too large to dismiss as a simple error. This tension has sparked intense debate among scientists. Some suggest that the discrepancy could be due to unknown systematic errors in our measurements. Perhaps our instruments aren't as precise as we think, or maybe there's something we're missing in the way we interpret the data. Others propose a more exciting possibility: that the Hubble tension is a sign of new physics, something beyond our current understanding of the universe. Could there be an undiscovered force or particle influencing the expansion rate? Or might dark energy, the mysterious force driving the universe's acceleration, be more complex than we've assumed? One intriguing theory is that the Hubble tension could be linked to the early universe. If the conditions in the first moments after the Big Bang were different than we've modeled, it could explain why the expansion rate measured from the cosmic microwave background doesn't align with observations of the present-day universe. Another idea is that our local region of the universe might be unusual, with peculiar gravitational effects skewing our measurements. While these theories are speculative, they highlight how the Hubble tension is pushing scientists to rethink their assumptions and explore new frontiers in cosmology. As we continue to investigate this mystery, one thing is certain: the Hubble tension is more than just a technical disagreement. It's a window into the unknown, a challenge to our understanding of the cosmos that could lead to groundbreaking discoveries. Whether it reveals flaws in our measurements or uncovers entirely new physics, it reminds us that the universe is far more complex and fascinating than we ever imagined. Next, we'll explore another cosmic puzzle, the missing baryons, a mystery that asks where a significant portion of the universe's ordinary matter has gone. How can something so fundamental simply vanish? Now, shifting our gaze to another cosmic enigma, we arrive at the mystery of the missing baryons. This puzzle revolves around a startling realization. A significant portion of the universe's ordinary matter seems to have vanished without a trace. Baryons, the building blocks of atoms, make up everything we can see: stars, planets, galaxies, and even ourselves. Yet, when scientists tally up all the baryonic matter in the universe, they find that a substantial amount is unaccounted for. Where could it be hiding? To grasp the scale of this mystery, let's start with what we know. According to the standard model of cosmology, baryonic matter should make up about 5% of the universe's total mass and energy. But when astronomers measure the amount of visible matter in galaxies and clusters, they find only about half of what's predicted. The rest, it seems, has gone missing. This discrepancy is known as the missing baryon problem, and it's one of the most perplexing challenges in modern astrophysics. So, where could this missing matter be? One leading theory suggests that it's hiding in the vast, diffuse regions of space between galaxies, in the form of warm, hot intergalactic medium, or WIM. This elusive material is thought to consist of ionized gas, so hot and thinly spread that it's nearly invisible to our telescopes. Detecting it requires looking for faint traces of ultraviolet or X-ray emissions, which is no easy task. While some evidence of the WIM has been found, it still doesn't account for all the missing baryons, leaving scientists to wonder if there's more to the story. Another possibility is that the missing matter exists in structures we haven't yet observed, such as faint dwarf galaxies or massive filaments of gas connecting galaxy clusters. These structures could be too dim or too diffuse to detect with current technology, making them effectively invisible to us. Alternatively, some researchers have proposed that the missing baryons might be locked up in exotic forms, such as primordial black holes or dark matter particles that interact weakly with ordinary matter. While these ideas are speculative, they highlight the creative ways scientists are trying to solve this cosmic puzzle. The missing baryon problem isn't just a technical challenge, it's a reminder of how much we still have to learn about the universe. If we can't account for all the ordinary matter, how can we hope to understand the more mysterious components like dark matter and dark energy? Solving this mystery could provide crucial insights into the structure and evolution of the cosmos, shedding light on everything from galaxy formation to the ultimate fate of the universe. As we continue to search for answers, one thing is clear: the universe is full of surprises, and the missing baryons are just one piece of a much larger puzzle. Next, we'll venture into another cosmic oddity, the Boötes Void, a vast, nearly empty region of space that defies our expectations of how the universe should look. What could explain this strange, desolate expanse? Now, let's turn our attention to one of the most baffling voids in the cosmos, the Boötes Void. Imagine a region of space so vast and empty that it feels like a cosmic desert, stretching across hundreds of millions of light years. This is the Boötes Void, a mysterious expanse that challenges our understanding of how the universe is structured. Unlike the dense clusters of galaxies we're used to seeing, this void is eerily sparse, containing only a handful of galaxies where we might expect thousands. How did such a colossal emptiness come to be, and what does it tell us about the universe? The Boötes Void, named after the constellation in which it lies, was first discovered in the 1980s. Astronomers were mapping the distribution of galaxies when they stumbled upon this enormous gap, spanning roughly 330 million light-years across. To put that into perspective, if the Milky Way were placed at one edge of the void, it would take light traveling at the fastest speed possible, over 300 million years to reach the other side. Yet, within this immense space, only about 60 galaxies have been detected, a number shockingly low compared to the density of galaxies in other regions of the universe. So, what could explain this strange emptiness? One theory suggests that the Boötes Void formed as a result of cosmic inflation, the rapid expansion of the universe just moments after the Big Bang. During this period, tiny fluctuations in density could have led to some regions becoming incredibly dense, while others, like the Boötes Void, ended up almost entirely empty. Another possibility is that the void is the result of smaller voids merging over billions of years, creating a single, massive region of emptiness. However, neither theory fully explains why the void contains so few galaxies, leaving scientists to wonder if there's more at play. The existence of the Boötes Void also raises questions about the large-scale structure of the universe. According to the cosmological principle, the universe should appear roughly the same in all directions, with matter distributed evenly on the largest scales. Yet, the Boötes Void defies this expectation, presenting a stark contrast to the dense web of galaxies and clusters we see elsewhere. This anomaly challenges our models of cosmic evolution and forces us to reconsider how matter is distributed across the universe. Could there be other voids like this, or is the Boötes Void a rare cosmic oddity? As we ponder these questions, the Boötes Void serves as a humbling reminder of how much we still don't know about the cosmos. Its vast emptiness is a testament to the universe's complexity and its ability to surprise us at every turn. Next, we'll explore another cosmic mystery, the Kuiper Cliff, a sudden drop-off in objects at the edge of our solar system. What lies beyond this mysterious boundary, and what secrets does it hold? Now, let's venture to the edge of our solar system, where another cosmic mystery awaits, the Kuiper Cliff. This strange boundary marks a sudden and dramatic drop-off in the number of objects beyond the Kuiper belt, a region filled with icy bodies and dwarf planets like Pluto. For decades, astronomers expected to find a gradual decrease in objects as they moved farther from the Sun. Instead, they discovered something far more puzzling, a sharp cutoff, as if the Kuiper belt abruptly ends, leaving a vast, empty expanse beyond. What could cause such a sudden disappearance of objects, and what might lie in the uncharted territory beyond this cliff? The Kuiper belt itself is a fascinating region, stretching from the orbit of Neptune out to about 50 astronomical units from the Sun. It's home to countless icy remnants from the early solar system, offering clues about how planets formed. But beyond this belt, at around 50 astronomical units, the number of objects drops off sharply. This boundary, known as the Kuiper Cliff, has left scientists scratching their heads. Why would the population of objects decline so abruptly? One possibility is that gravitational interactions with Neptune or other large bodies could have cleared out this region over billions of years. However, this explanation doesn't fully account for the starkness of the drop-off, leading some to propose more intriguing theories. One compelling idea is that the Kuiper Cliff might be the result of an unseen object lurking in the outer reaches of the solar system. Could a hidden planet, perhaps the elusive Planet 9, be responsible for sweeping this region clean? Some researchers suggest that the gravitational influence of a massive, undiscovered planet could have disrupted the orbits of objects beyond the Kuiper belt, creating the cliff we observe today. While this theory is still speculative, it adds an exciting layer of mystery to the search for Planet 9 and the secrets of our solar system's outer limits. Another possibility is that the Kuiper Cliff marks the edge of the primordial disk of material from which the solar system formed. If the disk had a sharp boundary, it could explain why objects become scarce beyond this point. Alternatively, the cliff might be evidence of a past event, such as a close encounter with another star, which could have stripped away objects from the outer solar system. Each of these theories offers a different perspective on the Kuiper Cliff, but none have been definitively proven, leaving this boundary as one of the most intriguing puzzles in our cosmic neighborhood. The Kuiper Cliff not only challenges our understanding of the solar system's formation, but also raises questions about what lies beyond. Could there be undiscovered objects or even entirely new regions waiting to be explored? As we continue to study this mysterious boundary, it reminds us that even our own solar system holds secrets we have yet to uncover. Next, we'll turn our attention to another interstellar enigma, the Oumuamua object, a visitor from beyond our solar system that left scientists with more questions than answers. Now, shifting our gaze beyond the boundaries of our solar system, we encounter one of the most perplexing cosmic visitors in recent memory, the Oumuamua object. Discovered in October 2017, Oumuamua became the first known interstellar object to pass through our solar system, sparking both excitement and intense debate among scientists. Its name, which means scout or messenger in Hawaiian, reflects its origins from another star system, but its true nature remains shrouded in mystery. What made Oumuamua so extraordinary was its unusual shape and behavior. Unlike typical asteroids or comets, which are often round or irregular, Oumuamua appeared to be elongated, resembling a cigar or a pancake. Even more intriguing was its acceleration as it moved away from the Sun. While most objects slow down as they leave the Sun's gravitational influence, Oumuamua sped up, defying the expectations of astronomers. This unexpected behavior led to a flurry of theories, ranging from natural explanations to more speculative ideas. One possibility is that Oumuamua was a comet, with outgassing the release of gas as it warmed near the Sun, causing its acceleration. However, no visible coma or tail, typical signs of cometary activity, were observed. This absence left scientists puzzled, as it suggested that if Oumuamua was a comet, it was unlike any they had seen before. Another theory proposed that it could be a fragment of a larger object, perhaps shattered by a collision or tidal forces from a distant star. Yet, even this explanation struggles to account for its peculiar shape and motion. The most controversial hypothesis, however, is that Oumuamua might not be a natural object at all. Some researchers, including Harvard astronomer Avi Loeb, have suggested that it could be an artificial construct, such as a light sail propelled by radiation pressure. This idea, while captivating, remains highly speculative and has sparked heated debates within the scientific community. Critics argue that extraordinary claims require extraordinary evidence, and so far, no definitive proof supports the artificial origin theory. Still, the possibility invites us to consider whether we might have encountered a piece of alien technology, a thought that both excites and challenges our understanding of the universe. As Oumuamua continues its journey into interstellar space, it leaves behind more questions than answers. Was it a comet, an asteroid, or something entirely different? Could it be a messenger from another civilization, or simply a natural object behaving in ways we don't yet understand? Whatever the truth, Oumuamua has reminded us that the universe is full of surprises. and that even the most fleeting visitors can spark profound questions about our place in the cosmos. Next, we'll explore another cosmic anomaly, the Eridanus supervoid, a vast emptiness in space that challenges our understanding of the universe's structure. Now, let's turn our attention to one of the most baffling regions of space, the Eridanus supervoid. This enormous, nearly empty expanse, located in the constellation of Eridanus, stretches over an astonishing 1 billion light-years across. To put that into perspective, it's so vast that if you were to travel through it at the speed of light, it would take you 1 billion years to cross from one side to the other. But what makes this supervoid truly mysterious is its connection to another cosmic oddity, the cold spot in the cosmic microwave background. The cosmic microwave background, or CMB, is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. It's remarkably uniform, but there's one area that stands out, a patch of sky that's significantly colder than its surroundings. This anomaly, known as the cold spot, has puzzled scientists for years. One leading theory suggests that the Eridanus supervoid might be responsible. The idea is that as light from the CMB passes through the supervoid, it loses energy, causing the temperature to drop and creating the cold spot. But here's the catch: the supervoid alone doesn't seem large enough or empty enough to fully explain the cold spot's extreme temperature difference. This discrepancy has led some researchers to propose even more exotic explanations. One possibility is that the cold spot is evidence of a collision between our universe and another bubble universe in a multiverse scenario. While this idea is speculative, it highlights how the Eridanus supervoid and the cold spot challenge our understanding of the universe's structure. Another theory suggests that the supervoid might be part of a larger, more complex cosmic web, with filaments of dark matter and gas influencing the CMB in ways we don't yet fully grasp. Whatever the explanation, the Eridanus supervoid and the cold spot remind us that even the emptiest regions of space can hold profound secrets. As we continue to study these cosmic anomalies, we're left with more questions than answers. Why is the Eridanus supervoid so vast and empty? What's the true nature of the cold spot, and how are these two phenomena connected? These mysteries push the boundaries of our knowledge, inviting us to rethink our understanding of the universe's origins and structure. Next, we'll delve into another cosmic puzzle, the discovery of a galaxy that appears to lack dark matter, challenging one of the fundamental pillars of modern astrophysics. Now, shifting our gaze to another cosmic enigma, we encounter a discovery that has left scientists scratching their heads, a galaxy that seems to defy one of the most fundamental principles of astrophysics. This galaxy, known as NGC 1052DF2, appears to lack dark matter entirely. Dark matter, as we know, is the invisible glue that holds galaxies together, making up roughly 85% of the universe's total mass. Without it, galaxies as we understand them simply shouldn't exist. Yet, here we have NGC 1052DF2, a galaxy that challenges this very notion. The discovery of this peculiar galaxy was first reported in 2018, and it immediately sparked intense debate. How could a galaxy form and maintain its structure without dark matter? To put it simply, dark matter's gravitational pull is what keeps stars, gas, and dust from flying apart. Without it, galaxies would disintegrate, but NGC 1052DF2 doesn't just exist, it thrives. Its stars move at speeds that suggest there's little to no dark matter influencing their motion. This finding has forced scientists to reconsider how galaxies form and evolve. One theory suggests that NGC 1052DF2 might have lost its dark matter through a cosmic collision. Imagine two galaxies passing close to each other, with the gravitational forces stripping away the dark matter from one of them. Another possibility is that this galaxy formed in a unique environment, perhaps within a cluster of galaxies where interactions could have removed its dark matter. However, these explanations are still speculative, and the true nature of this galaxy remains a mystery. What makes this discovery even more intriguing is that it challenges the very foundation of our understanding of the universe. Dark matter isn't just a minor component, it's the backbone of cosmic structure. If galaxies can exist without it, what does that mean for our current models of the universe? Could there be other galaxies like NGC 1052 DF2 hiding in plain sight, waiting to be discovered? These questions push the boundaries of astrophysics, inviting us to rethink what we thought we knew about the cosmos. As we continue to explore the universe, discoveries like NGC 1052 DF2 remind us that there's still so much we don't understand. Each mystery we uncover not only deepens our knowledge but also raises new questions, driving us to look further and dig deeper. Next, we'll turn our attention to the intricate structure of the cosmic web, the vast network of dark matter and gas that connects galaxies across the universe, and why its formation remains one of the greatest puzzles in cosmology. Now, let's unravel one of the most intricate and awe-inspiring structures in the universe, the cosmic web. Picture the universe not as a random scattering of galaxies, but as a vast, interconnected network, like a spider's web stretching across the cosmos. This web is made up of filaments of dark matter and gas, forming the backbone of the universe's large-scale structure. These filaments act as cosmic highways, connecting galaxies and galaxy clusters across unimaginable distances. But how does such a complex and delicate structure come to exist? And why does its formation remain one of the greatest unsolved mysteries in cosmology? The cosmic web is a direct result of the universe's evolution, shaped by the forces of gravity and dark energy. In the early universe, tiny fluctuations in density ripples left over from the Big Bang began to grow. Over billions of years, gravity pulled matter into dense regions, forming the filaments we see today. Dark matter, invisible and mysterious, played a crucial role in this process, acting as the scaffolding upon which ordinary matter, gas, stars, and galaxies could gather. Yet, despite our understanding of these basic principles, the exact mechanisms behind the web's formation remain elusive. How do these filaments maintain their delicate balance? And what determines their intricate patterns? One of the biggest challenges in studying the cosmic web is its sheer scale. The filaments span billions of light years, making them difficult to map in detail. Even with advanced telescopes and simulations, we've only begun to scratch the surface of this colossal structure. What we do know is that the cosmic web isn't just a static framework, it's a dynamic, ever-changing network. Gas flows along these filaments, feeding galaxies and fueling star formation. In some regions, the web is dense and bustling with activity, while in others it stretches into vast, empty voids. This interplay between structure and emptiness is what gives the universe its unique texture. But here's where things get even more puzzling. While simulations can recreate the cosmic web's general shape, they often struggle to match the fine details observed in the real universe. For instance, the distribution of galaxies along the filaments doesn't always align with predictions. Some filaments appear thicker or more diffuse than expected, while others seem to vanish entirely. These discrepancies suggest that there's still much we don't understand about the forces shaping the cosmic web. Could there be unknown factors at play, such as interactions between dark matter and dark energy? Or are we missing something fundamental about the universe's early conditions? The cosmic web isn't just a scientific curiosity, it's a key to understanding the universe's past, present, and future. By studying its structure, we can learn more about how galaxies form and evolve, how matter is distributed across the cosmos, and even how the universe might end. Yet, for all its importance, the cosmic web remains a mystery, a reminder of how much we still have to discover. As we continue to explore this vast network, we're not just mapping the universe, we're uncovering the story of its creation. With a cosmic web still holding so many secrets, our journey through the mysteries of the universe takes us next to another perplexing puzzle, the lithium problem. Why is there so much less lithium in the universe than our models predict? And what does this discrepancy tell us about the early moments of cosmic history? Now, shifting our gaze to a mystery that lies at the very heart of the universe's elemental makeup, we encounter the lithium problem. This puzzle revolves around a surprising discrepancy. The amount of lithium we observe in the universe is far less than what our scientific models predict. It's a cosmic riddle that challenges our understanding of nucleosynthesis, the process by which elements are formed in the early universe. To grasp the significance of this mystery, let's rewind to the moments just after the Big Bang. During this period, known as Big Bang nucleosynthesis, the universe was a seething cauldron of energy and particles. As it expanded and cooled, protons and neutrons began to combine, forming the lightest elements: hydrogen, helium, and trace amounts of lithium. According to our calculations, this process should have produced a specific amount of lithium, which we can predict with remarkable precision. Yet, when we look at the oldest stars in the universe, those that formed shortly after the Big Bang, we find that they contain only about 1/3 of the lithium we expect. Where did the rest go? This discrepancy isn't just a minor oversight. It's a glaring inconsistency that calls into question our understanding of the early universe. One possibility is that our models of Big Bang nucleosynthesis are incomplete. Perhaps there's a missing piece of physics that we haven't yet accounted for, something that could explain why less lithium was produced than predicted. Another theory suggests that lithium might have been destroyed over time, either through interactions with cosmic rays or through processes within stars themselves. But if that's the case, why don't we see evidence of this destruction in younger stars? The lithium problem also has implications for our understanding of stellar evolution. Stars are like cosmic laboratories where elements are forged and transformed. If our models of nucleosynthesis are flawed, it could mean that we're missing crucial details about how stars work and how they shape the chemical composition of the universe. This mystery isn't just about lithium, it's about the very foundations of astrophysics. As we continue to probe this enigma, new observations and advanced simulations are shedding light on possible solutions. Some researchers are exploring the idea that lithium might be hiding in regions of the universe we haven't yet observed, while others are revisiting the fundamental physics of the Big Bang. Whatever the answer, the lithium problem reminds us that even the smallest discrepancies can lead to profound insights. It's a testament to the fact that the universe still holds many secrets waiting to be uncovered. With the lithium problem still unresolved, our exploration of the universe's mysteries takes us next to another fascinating phenomenon: fast radio bursts. These intense bursts of radio waves from deep space have puzzled scientists for years, and their origins remain one of the most tantalizing questions in modern astronomy. Now, let's turn our attention to one of the most electrifying mysteries in modern astronomy: fast radio bursts. These are incredibly powerful bursts of radio waves that last just milliseconds, yet they release as much energy as the sun does in decades. First detected in 2007, these fleeting signals have since captivated scientists and amateur stargazers alike, not just for their sheer intensity, but for the fact that their origins remain shrouded in mystery. Imagine a signal so brief that if you blinked, you'd miss it, yet so powerful that it can travel billions of light years across the universe to reach us. Fast radio bursts, or FRB, are exactly that. They appear randomly in the sky, and while some repeat, most are one-off events, making them incredibly difficult to study. The challenge lies not just in detecting them, but in pinpointing where they come from. Are they the result of cataclysmic cosmic events, or could they be messages from advanced civilizations? The possibilities are as vast as the universe itself. One of the leading theories suggests that FRBs originate from highly magnetized neutron stars known as magnetas. These stellar remnants are among the most extreme objects in the universe, with magnetic fields trillions of times stronger than Earth's. When a magneta undergoes a sudden release of energy, perhaps due to a starquake or a magnetic reconnection, it could produce a burst of radio waves intense enough to be detected across the cosmos. But while this explanation fits some observations, it doesn't account for all FRBs, especially those that repeat. Another intriguing possibility is that FRBs are produced by collisions between dense objects, such as neutron stars or black holes. These violent encounters could generate shockwaves that emit bursts of radio energy. Yet, even this theory has its limitations, as not all FRBs seem to align with such events. Some researchers have even speculated that FRBs could be artificial in origin, perhaps signals from advanced extraterrestrial civilizations. While this idea is tantalizing, it remains highly speculative, and the scientific community continues to search for natural explanations. What makes FRBs particularly fascinating is their potential to reveal secrets about the universe itself. As these bursts travel through space, they interact with the cosmic web, the vast network of gas and dark matter that connects galaxies. By studying how FRBs are distorted as they pass through this web, scientists can map the distribution of matter in the universe, shedding light on its large-scale structure. In a way, FRBs are like cosmic flashlights illuminating the hidden corners of the cosmos. Despite the progress made in recent years, fast radio bursts remain one of the most enigmatic phenomena in astronomy. New telescopes and advanced detection methods are helping scientists gather more data, but each discovery seems to raise more questions than answers. Why do some FRBs repeat while others don't? What causes their immense energy, and could they be linked to other cosmic mysteries we've yet to uncover? As we continue to unravel the secrets of fast radio bursts, one thing is certain: these fleeting signals remind us that the universe is full of surprises. And with every burst detected, we come one step closer to understanding the forces that shape our cosmos. Next, we'll explore another cosmic puzzle that has baffled scientists for decades: the Planet 9 hypothesis. Could there be a hidden giant lurking in the outer reaches of our solar system? Let's find out. Now, shifting our gaze closer to home, let's dive into one of the most tantalizing mysteries within our own solar system: the Planet 9 hypothesis. For centuries, we've mapped the planets orbiting our sun, but what if there's a hidden giant lurking in the icy outskirts, waiting to be discovered? This is the question that has sparked intense debate among astronomers and space enthusiasts alike. The idea of a ninth planet isn't new. Pluto once held that title until it was reclassified as a dwarf planet in 2006. But the Planet 9 hypothesis isn't about Pluto. Instead, it proposes the existence of a massive, undiscovered planet far beyond Neptune, in the distant reaches of our solar system. This hypothetical world, estimated to be up to 10 times the mass of Earth, could explain some peculiar patterns observed in the orbits of smaller objects in the Kuiper Belt, a region of icy bodies beyond Neptune. The evidence for Planet 9 comes from the unusual behavior of these distant objects. Many of them have highly elongated orbits that seem to cluster in a way that suggests the gravitational influence of a large, unseen body. Imagine a cosmic puppeteer subtly tugging on the strings of these icy worlds, guiding their paths in ways that defy expectations. This gravitational signature is what first led scientists to propose the existence of Planet 9. But if such a planet exists, why haven't we seen it yet? The answer lies in its distance. Planet 9, if it's out there, is thought to orbit the Sun at an average distance of about 600 times farther than Earth. At such a vast remove, it would reflect very little sunlight, making it incredibly faint and difficult to detect with current telescopes. To put it in perspective, it could take this planet between 10,000 and 20,000 years to complete a single orbit around the Sun. That's a long time to stay hidden. The search for Planet 9 has become a modern-day cosmic treasure hunt. Astronomers are using some of the most advanced telescopes and sky surveys to scan the outer solar system for any hint of this elusive world. While no direct observations have been made yet, the hunt has already led to the discovery of other distant objects, enriching our understanding of the solar system's outer reaches. Skeptics argue that the evidence for Planet 9 could be explained by other factors, such as the combined gravitational influence of smaller objects or even a statistical fluke. However, the hypothesis remains compelling, and the search continues to captivate the scientific community. If discovered, Planet 9 would not only rewrite our understanding of the solar system, but also provide new insights into the formation and evolution of planetary systems. As we ponder the possibility of this hidden giant, we're reminded that even in our own cosmic backyard, there are still secrets waiting to be uncovered. The hunt for Planet 9 is a testament to the enduring spirit of exploration and the boundless curiosity that drives us to look beyond the known. Next, we'll explore another profound mystery that challenges the very foundations of physics, the quantum gravity problem. How do we reconcile the seemingly incompatible worlds of quantum mechanics and general relativity? Let's find out. Now, let's venture into one of the most profound puzzles in modern physics, the quantum gravity problem. At the heart of this mystery lies a fundamental clash between two of the most successful theories in science, quantum mechanics and general relativity. While quantum mechanics governs the behavior of the smallest particles in the universe, general relativity describes the force of gravity and the structure of space-time on cosmic scales. Both theories work flawlessly within their own domains, but when it comes to combining them, the result is chaos. The challenge begins with their very foundations. Quantum mechanics operates on the principle of uncertainty, where particles exist in a haze of probabilities and can behave as both particles and waves. It's a world where the rules are counterintuitive and the smallest scales are governed by randomness. On the other hand, general relativity paints a smooth, deterministic picture of the universe, where gravity is the curvature of space-time caused by mass and energy. These two frameworks are like languages that don't translate well into one another, leaving scientists struggling to find a common ground. One of the most glaring conflicts arises when we try to understand what happens in extreme environments, like the center of a black hole or the moment of the Big Bang. In these scenarios, the immense gravitational forces described by general relativity collide with the quantum nature of particles, creating a breakdown in our understanding. For instance, at the singularity of a black hole, where gravity becomes infinitely strong, the laws of physics as we know them cease to make sense. Similarly, the Big Bang, which marks the birth of the universe, presents a moment where both quantum effects and gravitational forces would have been dominant. Yet, we have no theory that can fully describe what happened. Over the decades, physicists have proposed several approaches to bridge this gap. One of the most prominent is string theory, which suggests that particles are not point-like objects but tiny, vibrating strings. These strings exist in higher dimensions, and their vibrations give rise to the particles and forces we observe. String theory offers a potential framework for unifying quantum mechanics and gravity, but it remains unproven and highly complex, with no experimental evidence to support it yet. Another approach is loop quantum gravity, which attempts to quantize spacetime itself. Instead of viewing spacetime as a smooth continuum, this theory proposes that it's made up of tiny, discrete loops. These loops weave together to form the fabric of the universe, offering a way to reconcile quantum mechanics with gravity. While promising, this theory also faces significant challenges and has yet to be confirmed by observations. The search for a theory of quantum gravity is not just an academic exercise, it's a quest to understand the very fabric of reality. Without it, we cannot fully explain some of the most extreme phenomena in the universe, nor can we answer fundamental questions about the nature of space, time, and existence itself. It's a problem that has stumped some of the greatest minds in physics, from Albert Einstein to Stephen Hawking, and it remains one of the most tantalizing mysteries in science. As we grapple with this challenge, we're reminded of how much we still have to learn about the universe. The quantum gravity problem is a testament to the complexity of the cosmos and the limits of our current understanding. But it's also a beacon of inspiration, driving scientists to push the boundaries of knowledge and explore the unknown. Next, we'll turn our attention to the ultimate question, the end of the universe. What fate awaits our cosmos and how might it all come to an end? Let's explore the possibilities. Now, as we turn our gaze toward the distant future, we confront one of the most profound questions in cosmology, the ultimate fate of the universe. What lies at the end of time itself? Scientists have proposed several compelling theories, each painting a vastly different picture of how the cosmos might meet its end. Let's explore these possibilities, starting with the Big Freeze. In this scenario, the universe continues to expand indefinitely, driven by the relentless force of dark energy. Over trillions of years, galaxies will drift farther apart, stars will burn out, and the cosmos will grow colder and darker. Eventually, all that remains will be a vast, empty expanse where even black holes evaporate, leaving behind only a faint, fading glow of radiation. The Big Freeze is a chilling vision of a universe that simply fades into oblivion, a quiet and desolate end to all things. But what if the universe doesn't expand forever? Another possibility is the Big Crunch, a dramatic reversal of the Big Bang. In this scenario, the expansion of the universe slows down and eventually stops, pulled back by gravity. Galaxies, stars, and even atoms would collapse inward, compressing everything into an infinitely dense point, a cosmic singularity. This fiery end would mirror the birth of the universe, but in reverse, as all matter and energy are crushed together in a final, cataclysmic event. Then there's the Big Rip, a more violent and sudden demise. If dark energy grows stronger over time, it could eventually overpower all other forces in the universe. Galaxies, stars, planets, and even atoms would be torn apart as the fabric of spacetime itself is ripped to shreds. The Big Rip is a terrifying prospect where the universe is literally pulled apart at every level, leaving nothing but a chaotic void in its wake. So, why can't we predict which of these fates awaits us? The answer lies in the uncertainty surrounding dark energy, the mysterious force driving the universe's expansion. We don't yet understand its true nature or how it might change over time. Without this knowledge, we can only speculate about the ultimate destiny of the cosmos. Each of these theories offers a glimpse into the profound mysteries of the universe, reminding us of how much we still have to learn. Whether the universe ends in a cold, silent fade, a fiery collapse, or a violent tear, one thing is certain: the story of the cosmos is far from over. And as we continue to explore these possibilities, we're reminded of the awe-inspiring complexity and beauty of the universe we call home. Next, we'll dive into a bonus mystery that challenges not just our understanding of the universe, but the very nature of reality itself, the simulation hypothesis. Could our universe be nothing more than an elaborate simulation? Let's explore this mind-bending idea. Now, let's venture into a mystery that challenges not just our understanding of the universe, but the very nature of reality itself. Could everything we know, our world, our lives, even the stars above, be nothing more than an elaborate simulation? This is the core of the simulation hypothesis, a theory that has sparked intense debate among scientists, philosophers, and thinkers alike. The idea isn't as far-fetched as it might sound. In fact, it's rooted in some compelling arguments. One of the most famous comes from philosopher Nick Bostrom, who proposed that if advanced civilizations could create simulations indistinguishable from reality, it's statistically likely that we're living in one. Think about it. If future humans or extraterrestrial beings develop the technology to simulate entire universes, the number of simulated realities could vastly outnumber the one base reality. So what are the odds that we're in the original? From a scientific perspective, some researchers have even looked for evidence that might support this idea. For instance, if our universe were a simulation, it might have certain glitches or limitations, like the pixelation of space at the smallest scales. Others have pointed to the strange behavior of particles in quantum mechanics, where things don't behave as expected unless they're being observed. Could this be a sign that the universe is running on some kind of computational framework? But not everyone is convinced. Critics argue that the simulation hypothesis is untestable and more of a philosophical thought experiment than a scientific theory. After all, how could we ever prove we're in a simulation if the simulation itself controls all our perceptions and tools of measurement? Some also point out that creating a universe-sized simulation would require an unimaginable amount of energy and computational power, far beyond anything we can currently conceive. Yet the idea continues to captivate us because it forces us to question the very fabric of existence. If we are living in a simulation, what does that mean for free will, consciousness, and the purpose of life? Are we merely characters in someone else's program, or do we still hold agency within this constructed reality? The simulation hypothesis doesn't just challenge our understanding of the universe, it challenges our understanding of ourselves. Whether you find it fascinating, unsettling, or downright unbelievable, it's a mystery that pushes the boundaries of science and philosophy, inviting us to rethink everything we thought we knew about reality. As we ponder this mind-bending possibility, let's turn our attention to another mystery that delves even deeper into the nature of existence, the enigma of consciousness itself. What is it, where does it come from, and could it hold the key to understanding the universe? Let's explore this next. Now, let's shift our focus to one of the most profound mysteries of all, the nature of consciousness. What is it that makes us aware of ourselves and the world around us? Is consciousness merely a byproduct of the brain's complex processes, or could it be something far more fundamental, woven into the very fabric of the universe? At its core, consciousness is the experience of being the thoughts, feelings, and sensations that make up our inner world. Yet, despite centuries of study, scientists and philosophers still struggle to explain how something as intangible as consciousness arises from the physical matter of the brain. This is known as the hard problem of consciousness, a term coined by philosopher David Chalmers. The hard problem asks why and how physical processes in the brain give rise to subjective experience. Why does seeing the color red feel a certain way, or why does pain hurt? These questions remain unanswered. Some theories suggest that consciousness might be a fundamental property of the universe, much like space, time, or gravity. This idea, known as panpsychism, proposes that even the smallest particles possess some form of basic awareness. While it might sound strange, panpsychism offers a way to bridge the gap between the physical and the experiential, suggesting that consciousness isn't something that emerges from complexity, but is instead a fundamental feature of reality itself. On the other hand, materialist theories argue that consciousness is entirely a product of the brain's neural activity. According to this view, when neurons fire in specific patterns, they create the illusion of a unified self and subjective experience. But this raises another question. If consciousness is just a result of brain activity, could it be replicated artificially? Could a sufficiently advanced computer or robot ever become truly conscious? The mystery deepens when we consider altered states of consciousness, such as those experienced during meditation, near-death experiences, or under the influence of psychedelics. These states often lead to profound insights and a sense of interconnectedness with the universe, challenging our conventional understanding of reality. Could these experiences hint at a deeper, more universal form of consciousness that transcends individual minds? Some scientists have even speculated that consciousness might play a role in shaping the universe itself. Quantum mechanics, for example, suggests that particles exist in a state of probability until they are observed. Could consciousness be the force that collapses these probabilities into definite outcomes? While this idea remains highly controversial, it opens the door to the possibility that consciousness isn't just a passive observer but an active participant in the cosmos. As we explore these theories, one thing becomes clear: consciousness is not just a scientific puzzle but a deeply philosophical one. It challenges us to rethink our place in the universe and the nature of reality itself. Whether it's a product of the brain, a fundamental property of the cosmos, or something else entirely, consciousness remains one of the greatest mysteries we have yet to unravel. With this in mind, let's turn our attention to another fascinating concept that pushes the boundaries of our understanding: the holographic principle. Could the universe itself be a projection, with all its information encoded on a two-dimensional surface? Let's dive into this next mystery. Now, let's venture into a concept that sounds like it belongs in a science fiction novel, but is grounded in serious scientific inquiry: the holographic principle. Imagine for a moment that everything we see, touch, and experience in our three-dimensional world might actually be a projection from a two-dimensional surface. Sounds mind-bending, doesn't it? Yet, this is precisely what the holographic principle suggests: a radical idea that challenges our understanding of reality itself. The holographic principle stems from the study of black holes and the nature of information. When an object falls into a black hole, it seems to disappear forever, but this creates a paradox. According to the laws of physics, information cannot be destroyed. So, where does it go? Physicists Leonard Susskind and Gerard T. Hooft proposed that the information isn't lost but is instead encoded on the black hole's event horizon, the boundary beyond which nothing can escape. This idea led to the broader theory that the entire universe might operate in a similar way, with all the information about our three-dimensional reality stored on a two-dimensional surface. Think of it like a hologram. A hologram is a two-dimensional image that, when illuminated, creates the illusion of a three-dimensional object. In the same way, the holographic principle suggests that our universe could be a kind of cosmic hologram, with all the complexity of space, time, and matter encoded on a flat, two-dimensional boundary. This boundary could be something like the edge of the observable universe or even the surface of a black hole. But how could this possibly work? One way to understand it is through the concept of entropy, a measure of disorder or information. In black holes, entropy is proportional to the area of the event horizon, not the volume of the black hole itself. This hints that the fundamental bits of information in the universe might be tied to surfaces rather than volumes. If true, it would mean that the three-dimensional world we perceive is, in a sense, an illusion, a projection of information stored on a two-dimensional plane. The implications of the holographic principle are staggering. If the universe is a hologram, it would mean that everything we know, galaxies, stars, planets, even our own bodies, are essentially encoded on a flat surface. This idea has profound consequences for our understanding of space, time, and the very nature of reality. It could even provide a pathway to unifying quantum mechanics and general relativity, two theories that have so far resisted reconciliation. However, the holographic principle is not without its challenges. For one, it's incredibly difficult to test experimentally. While there are mathematical models that support the idea, we lack the technology to directly observe or measure this two-dimensional encoding. Additionally, the principle raises philosophical questions about the nature of perception and existence. If reality is a projection, what does that mean for our sense of self and our place in the cosmos? Despite these challenges, the holographic principle continues to captivate scientists and thinkers alike. It represents a bold attempt to reconcile some of the deepest mysteries of the universe, from the behavior of black holes to the fundamental nature of space and time. Whether it ultimately proves to be true or not, it pushes the boundaries of our imagination and challenges us to rethink what we know about reality. As we ponder this extraordinary idea, let's turn our attention to the final mystery on our list, the ultimate fate of the universe. What lies ahead for the cosmos and how might it all end? Let's explore this next. As we reach the end of our journey through the 25 mysteries of the universe, it's clear that the cosmos is far more enigmatic than we often realize. From the invisible grip of dark matter and dark energy to the mind-bending possibilities of the multiverse and the holographic principle, each mystery challenges our understanding of reality in profound ways. We've explored the unanswered questions surrounding the Big Bang, the eerie silence of the Fermi paradox, and the strange behavior of black holes. We've pondered the nature of time, the mysteries of quantum entanglement, and the cosmic anomalies like the Great Attractor and the Boötes Void. Each of these mysteries reminds us that the universe is a place of endless wonder, filled with puzzles that defy even our most advanced scientific theories. But the journey doesn't end here. These mysteries are not just scientific challenges, they are invitations to keep exploring, questioning, and imagining. They remind us that the universe is vast, complex, and full of surprises, and that there is still so much we have yet to discover. Whether it's the search for Planet 9, the origins of fast radio bursts, or the ultimate fate of the cosmos, each mystery pushes the boundaries of what we know and inspires us to look deeper. So, which of these mysteries fascinates you the most? Is it the eerie possibility of parallel universes, the haunting silence of the Fermi paradox, or the mind-bending idea that our reality might be a hologram? Let us know in the comments below. We'd love to hear your thoughts and theories. And if you've enjoyed this cosmic journey, don't forget to hit the like button, subscribe to our channel, and ring the notification bell so you never miss an exploration into the wonders of the universe. Thank you for joining us on this adventure through the mysteries that defy science and challenge our understanding of existence. Until next time, keep looking up and wondering, because the universe is full of secrets waiting to be uncovered.